Hi everyone, again, this is the second part of chapter 16. In the first part we covered the first 6 sections of the chapter, and now we're going to start at the 7th section, which is parallel capacitance. This chapter is basically a very high level explanation about what capacitance and capacitors are. And when we go into chapter 17 and chapter 18, that's when we're really going to start working with circuits that have capacitors in it. But let's go ahead and get started with this video, and we're going to cover parallel and series capacitance and how we calculate those. Okay, so connecting capacitance in parallel is equivalent to increasing the plate area. So if we have two capacitors that are connected in parallel, the voltage across both branches is going to be the same. So the same voltage is going through, it's going towards both capacitors. So therefore, we're using the same voltage to charge two different plates, for example, the positive or the negative end. And what we're actually doing, we're just increasing the area of the plates, because two plates together basically will make a bigger area. So that's why when we estimate to calculate the total capacitance of capacitors that are in series in parallel, we will add the capacitance. Okay, so parallel capacitance, we add the capacitance just the same way we used to do with resistor, but backwards, right? In resistors, it was the other way around. You will add the resistors when they're in series. With capacitors, you add the capacitors when they are in parallel. So because the voltage is the same across parallel capacitors, so basically the area that's being charged is increased. So you get more capacitance when you put it in parallel. On the other hand, when you have series capacitance, then you're going to calculate the equivalent capacitance of capacitors in series by doing 1 over the sum of the 1 over each capacitor, like on this formula right here. So connecting capacitors in series is equivalent to increasing the thickness of the dielectric. Therefore, that's the total capacitance of capacitors that are in series. The total must be less than the smallest individual value in the circuit. Okay, let me go ahead and do some show you how this can be applied in. Do some examples in here so you guys can see what we're talking about when we say series and parallel capacitors. All right, so let's let me move this around here. Okay, we have, for example, remember when we had resistors that were like in series, all right? So if we had a resistor like this and we have a voltage, this R1 and R2, they're in series, so RT equals R1 plus R2, right? And that would be when you use resistors. And if you have resistors in parallel like this, all right, you say that total resistor here, or the equivalent resistor, will be 1 over R1 plus 1 over R2. Or you can also say that this is R1 times R2 divided by R1 plus R2. Okay, this is nothing new. This is what you learn from chapter 1 through 14 in EET 1011. Okay, this is the equivalent resistance for two parallel resistors. And this one is the total resistance for two resistors in series. Okay, so now when we're dealing with capacitors, let's say, for example, we have Okay, this is gonna be C1 and this is gonna be C2. Okay, the reason why I did this capacitor with two lines, two straight lines, and one with one straight line and a curvy line like this is just to show you that this is exactly the same thing. Okay, but some literature, some books, they will show the capacitor like this, or they can show it like this, but that does not make a difference. At least to our level, it will not make a difference. Okay, so if we have a source, we have a circuit in which we have two capacitors in series like this, we do the opposite that we do when we have resistors. Okay, so the total, or let's say equivalent, the equivalent capacitance for this is gonna be 1 over C1 plus 1 over C2. Okay, if it's only two of them, then we can say that this is gonna be C1 times C2 divided by C1 plus C2. Okay, so as you can see, the total equivalent, so if we replace this by one with one capacitor, okay, this is gonna be V, so this one is gonna be the equivalent, okay, of these two. So this equivalent capacitor will have a capacitance that is less than the smallest one of these two. Okay, just like the resistors in parallel, the equivalent capacitance of series connected capacitors, the capacitance of this will be less than the individual ones. It is less than the smallest one of these two. Same as the resistors. Okay, when the resistors are connected in parallel, we use the same concept. So if we have a circuit in which the capacitors are connected in series, all right, let's say this is C1 and this is C2, and here we have the voltage applied. Okay, now that is a parallel circuit. All right, you have two capacitors in parallel, so when you do that, you can say that the total capacitance, or the equivalent capacitance, if you want to call it that way, it would be just C1 plus C2, just like the same thing as the circuits that are resistors in series. All right, so just remember that when you're dealing with resistors, serial resistors are, you can add them up. Okay, R1 plus R2, that will give you one circuit that may look like this. You can replace it with one resistor that will have the same voltage. I mean, one circuit with the same voltage, but you can replace these two with one resistor that's the sum of the two resistors in series. When you have resistance in parallel, right, what you do, you take 1 divided by the sum of the reciprocals of each resistor. Okay, so 1 divided by 1 over R1 plus 1 over R2. If we simplify this expression right here, we get R1 times R2 divided by R1 plus R2. They happen when you have only two resistors, okay, in parallel. Okay, so that would be the reference that you can have the resistors, the capacitors behave in the opposite way as the resistors. So the resistors in series, you get to add them up. Capacitors in series, you don't add them up. You do what you do with resistors in parallel. Okay, so that when you have capacitors in series, you're gonna do 1 over the reciprocal of each capacitance. Okay, so 1 over C1 plus 1 over C2, and you simplify these expressions, and you will get this right here if you're only dealing with two capacitors. So, and when you have the capacitors in parallel, you're going to use the formula that you're going to add the capacitance of both capacitors, okay? and because the two capacitors in parallel behave in the same way, well, mathematically you will do it the same way as you do the resistors in series. Okay, the reason why is because if you have a voltage applied here, so this voltage is the same voltage across the two capacitors. Okay, so the same voltage is charging both capacitors. Okay, and this capacitor has a plate here and has a plate here. Each one of these two plates have a area. This one does the same thing. So when you use this voltage to charge two capacitors in this way, what you're doing really is like if you were charging a huge capacitor that have these two plates together. So it's a bigger area, so you will accumulate more charge. Okay, because the area of the plates is going to be bigger. You actually sending the current here to these two plates, or the area that is being covered is bigger, so you just add up the capacitance. Okay, in this case it's different because instead of hitting the same voltage across each capacitor like here, you're doing this voltage is right here. So you have to use the voltage divider because this is going to take some of it and this is going to take some of it. Okay, the one with the smallest capacitance is the one that is going to take more voltage than the other one. So if C1 is less than C2, so C1 is going to capture more of this voltage. And we're going to see that when we do some numerical problems. So let's do a numerical problem right here so we can see. We can take a look at this problem on page, let's say page number 510 on your book, right? So it's the same. Let's see, we have a this circle right here, right? So in this, we're going to have a total voltage here of 1000 volts. C1 is going to be 1 microfarad, and C2 equals 1 microfarad as well. Okay, so we can find the equivalent capacitance for this. Okay, and we say that equivalent capacitance for these two will be 1 over 1 plus 1 over 1, because this is microfarad and this is microfarad as well, right? So basically in this one we're gonna have 1 over, this is gonna be 1 plus 1, that will be 2 over 1 microfarad, right? So that will be 1 microfarad divided by 2, and this is going to be 0.5 microfarads. All right. So that would be the equivalent. So we can replace this circuit with one capacitor only, and this one, let's say C equivalent would be 0.5 microfarad. See that? These two are the same, so the equivalent for these two will be half of that one. Okay, so this capacitor right here is equivalent to these two capacitors connected in series, and that's only half of the microfarad. All right. So let's do the same a different problem now with different capacitors, and we will find the voltage across the capacitors. Okay, let's say this one, C1 equals 1 microfarad, C2 equals 2 microfarad, right? And we're gonna have, let's say, the voltage right here, VT, would be 900 volts, right? 900 volts. So in order for us to find the voltage across each one of these capacitors, we have to find, so we need to find what is the voltage here and here. Okay. So let's see what's the voltage across C1, okay? VC1. Okay, so this is the total voltage. Across here is 900 volts, right? So if we do the voltage divider here, so we're gonna say that C1 is gonna be C2 divided by C1 plus C2 multiplied by the total voltage. Okay, so this is going to be, if we keep it as microfarad, that would be 2 divided by 1 plus 2 times 900, right? So this is going to be 2 divided by 3 times 900 volts, and that will give you 600 volts, right? So the voltage across this right here will be 600 volts, right? Therefore, if it's 900, you get 600 here, so the voltage across here would be 300. Okay. Hopefully you guys remember how to use the voltage divider. Okay. So let's say we're gonna do VC2, the voltage across this one. So it's gonna be C1 divided by C1 plus C2 times the total voltage of VT, and that's gonna be 1 divided by 3 again times 900, and that will give you 300 volts. All right. So if you're having problems, remember in this, please remind me during the lab session so I can do a small lecture on the voltage dividers. Okay, because this is very, very important. You learned this back in chapter 13 or 14, where you were talking about, you know, DC voltages and all that stuff. You know, so the voltage divider don't really, they don't, what is it? They don't. They're no different if you're doing it with the AC or the DC. Okay, so in this case right here. Okay, so this is 900 volts applied to this series, okay, of capacitors. Okay, so this voltage have to be divided between these two items right here. Okay, so we use the voltage divider rule, which says that if we're gonna find the voltage across this one right here, so we say this one divided by the total and then multiply by the source, and that gives you the voltage on the C1. And the same thing we do for the next one. Okay, to find the voltage across C2. All right. Now let's do an example with a parallel circuit. Okay. Let's say you have a circuit that has two if we have a circuit that has two of the capacitors in parallel. Okay, so remember, these are parallel, right? So if we have a voltage here, whatever the voltage is, this voltage right here is the same voltage here, all right? And this is connected in parallel. Remember, this is just the wire. I mean, this one could be in the front of it. That doesn't matter, you know? So the whole thing, this is like considered like one big node right here, all right? And this is another big node, ground, right? So this voltage is across the two capacitors with no difference. Okay, so if we need to find, for example, if we want to find the equivalent capacitor here, then let's say this is a, let's say 2 microfarad, and this is, let's say 3 microfarads, right? So to find this one, the capacitor that is the total capacitance, we just add 2 plus 3 equals 5 microfarads. All right, and that would be the end of it. How to find the equivalent or the total capacitance when you have two capacitors in parallel like this one. So let me go back to the PowerPoint. All right, so capacitors, just like any other, just like resistors, they can be measured as well. So there's measuring equipment and equipment that you can use to test capacitors. And this is the capacitance meter. So when we measure in capacitors, please, we have to make sure that these capacitors are discharged all the way before you apply in the meter, okay? Because you cannot measure the capacitor when it's charged, okay? That may cause a electric shock or something, all right? It is important to know conversions as well, okay? When you're working with capacitors, because the capacitors have capacitance that are in a very, very small amounts, when it comes to farads, we'll be talking about microfarads, we'll be talking about picofarads. So it's always recommended that we remember how to do the conversions for nano units to pico units to micro units to milli units. And that was covered in the introductory chapter of this book, before chapter 1, when you took EET1021, the powers of tens, okay? So if you're having problem with that, please go back to that chapter and just do a quick review on how to make conversions of powers of tens, okay? Because the equipment, the meters where you're gonna be measuring the capacitance of capacitors, they do not measure in nanofarads. They can do picofarads or microfarads, but not nanofarads. So you have to make the conversion there. You have to be able to make the conversion when you plug the equipment in it, and it will tell you, it will give you a value in picofarads or nanofarad or microfarads. So if you need to express your answer in nanofarads, then you have to remember how to do those conversions, okay? Now, when we talk about capacitors on circuits, we always refer to capacitors as ideal devices, ideal elements, okay? But there is no such thing. So when the capacitor is charged, there is always, and when it's charged and when we disconnect the source, there is always a small leakage of charge on the capacitors. They can even leak through the air. So it's very small, but they do discharge. So they're not perfect, okay? So we have to take all those things into consideration when we actually doing practical problems. Most of the problems that we'll be doing here, though, they're gonna be ideal problems, so we don't have to worry so much about the leakage. Now, when you take some advanced, some very advanced courses in electronics, then that's when you will be talking about calculating this leakage and all that. But let's do a quick high-level review on these leakages. Okay, there is 3 ways the capacitor can leak the charge that is in it. Okay, so these 3 ways can be represented as the equivalent series resistance. Okay, which, let me see if I can get a diagram here. Let's see. So the capacitors can leak through the dielectric. They can also leak through the across the insulated cases or body between the capacitors. The case where the capacitors have some kind of contact with between the leads, and then that causes leakage, and also through the air. Because remember, the air is also a dielectric, so it could be discharged just by sitting there. Okay, depends on the quality of the capacitors. And each one of these things will have an equivalent. I mean, if we combine all this leakage in one, we will get what is the total losses. The total losses of or the total leakage. We can represent that in the diagram with a circuit like this. This is let's say the ideal capacitor, then we can represent leakages. They can leak through resistors like this, okay? And then this would be like for the case of the capacitor, this could be through the dielectric not being able to release all the charge when it's discharged, and then that would cause a leakage on it, and then some other leakage, through the air. For example, instead of doing all this, we can always represent this capacitor with a equivalent series resistance. Okay, this is just this is just a graphical representation, just to have an idea how the capacitor leak. All right, so just remember the capacitors are charged, and they accumulate charge when they're fully charged. They're dangerous to handle, so we have to be very careful in the lab. During the lab session, we're going to cover more of these safety issues, and for now, so this marks the end of chapter 16. And as always, I want to thank you for your attention and the opportunity to serve you today. And soon I will be posting the chapter 17 lectures. Okay, for now, thank you, and until next time.